So there are two situations in which it's impossible to find the exact value of a definite integral. The first one is where we need to know an antiderivative of f, and it's not possible, like the integration of e to the x squared dx, like we talked about in the end of section 7.5. So that's not possible, but we know that the antiderivative is the area under the curve, so we could do that. The second one is if we have data from a scientific experiment and there's no formula for the function, and that's one of the ones we're going to look at. So in these two cases, then you definitely need another method. In Calc 1, when you learned area under the curve, you learned it using left midpoint and right midpoint, or left endpoint approximation and right endpoint approximation, and probably midpoint. And we're going to look at those and two more that are more exact. So here we have the left endpoint and the right endpoint and the midpoint, and there are the sums. The antiderivative equals the sum of the rectangles. And the midpoint rule, let me pull that for you. So here you can look back and see we did this in chapter 5 back in Calc 1 to find the left endpoint and the right endpoint. So we find the rectangles and add them together. And then we find the midpoint rule, and the midpoint approximation says I'm finding the midpoint between the x values. So you can see you have x1 bar, x2 bar, x3 bar, x4 bar. So let's look at an example here, and then we'll move into the other two types. I'm going to start with a nice parabola. Let's call it y equals x squared plus 3. So then they tell you how many rectangles or so forth to look at, and they're going to say let n equal 4. So let's go from 0 to 2. The interval is given to you. So that means here I have 1, and to have 4 rectangles, that means this is a half, and this one is 3 halves. So just a remembrance of Calc 1, if we do left endpoints, that means we draw lines. Well, I would recommend that you find all the points first. So take a minute and let's fill that in. This point right here is 1/2. And then a half squared is a fourth, plus 3 is 3 1/4. And that's 13/4. So fill in the rest of those points. 1 squared is 1, plus 3 is 4. 2 squared is 4, plus 3 is 7. That's the easy one. 3 halves squared is 9/4, plus 12/4 is 21/4. Okay, so the left endpoint, we should fill that in. Here I have 0, 3. So you have all of these points. Okay, now we're really ready. So left endpoint says I draw the line from the left endpoint all the way over. Now the change in x here is a half each time. This change in x is a half. And here I have a rectangle. And my change in x is my length, and then, or base, and then I have a height. It's kind of easier to think about it as base and height. So my base for each of these rectangles is a half, because that's the change in x. So now let's talk about this height. This first height is 3. So I have a half times 3. So technically, to find the area under the curve, I have a half times 3. Plus, I have a half times the second height has the height of 13/4. So we have a half times 13/4. Plus, the next one is a half, and the height is 4. You can see that here. And then the height is 21/4. So we have a half times 21/4. So there's several ways to do that. I would factor out the half. So you have 3 plus 13/4 plus 4 plus 21/4. So we add these up. So I have 12 over 4 plus 13 over 4 plus 16 over 4 plus 21 over 4. So we have 1/2 times 62 over 4, which is 31 over 4 for your area. Now, if you were to integrate this, we would integrate from 0 to 2. We have x squared plus 3 dx. So we integrate that. We have 1/3 x to the third plus 3x from 0 to 2. So we have 8/3 plus 6, which is 8 over 3 plus 18 over 3, which equals 26 over 3. 31 over 4 is what we found for approximation. That's a little less than 8, and 26 over 3 is a little more than 8, but notice we're under the curve, and you have all this space that's not accounted for. So your left and right approximations are not that great. But we're going to look at this problem several times and remember that 26 over 3 is really the area under the curve. The reason we learn other methods is, remember, not everything can be done because you don't always have a function or it's not something you have an antiderivative of. So that was a left endpoint. So let's look at the same problem with right endpoints. So right endpoints means I draw it like this. So I'm going to have to be careful about my heights here. So we come from the right. In this case, it's above the curve, so it's going to be an overestimation. And our change in x is still 1/2. So we say the area equals, can we put 1/2 out here? And the height of this rectangle is 13 over 4. Plus the height of this rectangle is 4. Plus the height of the third rectangle is 21 over 4. And the height of the last rectangle is 7. So we have 1/2, common denominator of 4, 28, 21, 16, 13. So this is 1/2 of 78 over 4, which is 39 over 4. Now that's nearly 10. And notice our real integration down here is 26 over 3, which is nearly 9. But this is an overestimate because it's over the curve. So those are the two methods you learned in Calc 1. And let's look at the midpoint method. We do learn the midpoint rule in Calc 1 because we learned that if we take 39 over 4 from our right bound and we take 31 over 4 from our left bound, and we average them, so we take half of that. That means we're really taking half of 70 over 4, which half of 70 is 35 over 4. 35 over 4 is nearly 9, so that's a whole lot closer to our 26 over 3. But we don't want to do all the left and right endpoints to get there. So what we do is we take the midpoint. So we start off with our same curve, but instead of using these values, we're going to use the midpoints. So the midpoint rule says I'm using the midpoint of these values, and that's my x is 1/4. And then the midpoint here is x is 3/4, so it about splits the difference on both the x and the y. So the x here is 5 over 4, and the x here is 7 over 4. So those are the x values, and you find the corresponding y values. So we have 1/4 and continue. So these are my x and y values. So again, our midpoint in this case, our change in x is still a half. So for the midpoint rule, you do the change in x, which is, in this case, it's a half, and we're going to add the 49, the y values that go with the midpoints. So we found x, the midpoint of 0.5 to be a fourth, and the y value for that's 49 over 16, plus 57 over 16, plus 73 over 16, plus 97 over 16. So if we add those, I have 276 over 16, which comes out to, if you take half of the top, we have 138 over 16, which is nearly 9 again. It's a better approximation if you look at the decimal values. This is a better approximation than the other. But it's still not our best option. But midpoint rule, you find the midpoints. And then you find the y values. And then you do area equals change in x times the sum of the y values. So if we go back to the midpoint rule, and it looks like this. So midpoint rule is one of the 3 methods you have to be able to do in this lesson. Let's look at the next one. This one is my favorite. It's the trapezoid rule. So remember, a trapezoid says that the 2 bases are not the same. So the trapezoid connects the endpoints like this. Now, it doesn't sit exactly on the curve like it looks like, but here we have base 1 and base 2. Remember that the trapezoid, when you were in geometry, looked like this. So you have base 1 and base 2, and the area is 1/2 height times base 1 plus base 2. So we're going to use that principle here as we find these. So our height is technically this length in here because you have parallel bases that are not equal. So that's base 1 and base 2, base 1 and base 2, base 1 and base 2. But as you can see, let me move this up. So our normal definition of a trapezoid says my height is perpendicular to my bases, and I have 1/2 height, base 1 plus base 2. Now look at the pattern here. We do 1/2 height because it's in every single term, and then have 1 plus base 2, and then I can technically call this base 2 and base 3. And then we have base 3 and base 4. And then we have base 4 and base 5. So base 1 plus base 2. And then in the second rectangle, I have base 2 repeated and I have base 3. And then the next rectangle, I have base 3 repeated and base 4. And then in the last rectangle, we have base 4 repeated and base 5. So notice the only single bases are base 1 and base 5. So you could say 1/2 height times base 1 plus 2 base 2 plus 2 base 3 plus 2 base 4 plus base 5. So what we're saying here is that base 2 is counted twice because it's in both the rectangle, the trapezoid before it and the trapezoid after. Base 3 is in there twice because of the trapezoid before and the trapezoid after. And base 4 is in there twice because of the trapezoid before and after. So when we do the math here, we say 1/2 height, and the height here is still our delta x, which is 1/2. So we have 1/2. By the way, the formula in your book, let me back up and do that. The formula in your book literally says delta x over 2. Let me tie this in for you. They say that delta x over 2, so that's the height divided by 2, And then they say f of x sub o plus 2 f of x sub 1 plus 2 f of x sub 2 plus dot 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 plus 2 f of x sub n minus 1 plus f of x sub n. So you can see that the first one and the last one happen once, and everything in the middle occurs twice. So now let's look at ours. Let's go back to here. We have area equals 1/2, and the height is 1/2. I tend to use 1/2 height because I'm comfortable with my trapezoid rule, and that works out easier for me. So my base 1 is my first y value of 3, plus 2 times base 2 is 13/4, plus 2 times base 3 is 4, plus 2 times base 4 is 21/4, plus base 5 is 7. Remember, your first one and your last one only get used once. Everything else occurs twice. So we have 1/4, 3, plus 26/4, plus 8, plus 42/4, plus 7. So let's add our whole numbers. 7 and 3 and 8 make 18, plus 70/4. Let's reduce that to 35/2. So now 36/2 plus 35/2 makes 71/2, which is 71/8. That's nearly 9. When we did the real integral, we got 26/3, which is 8.6 repeating. 71/8 is 8 and 7/8, which is 8.875. So we're just a little off, but it's a much closer approximation than we've had up until this point. So and I'm using numbers to show you that we're getting closer, but generally we do these problems because we can't integrate. We need a method to help us do it. So the trapezoid rule is an easy rule to use. You have 1/2 times the height, which is your change in x, and then you add all of the bases. The first one occurs once, the last one occurs once, and the ones in the middle occur twice. Now your book has a very technical definition. So here you can see the trapezoid rule, and you can see how it's not just the midpoints, it follows the curve more closely. So it is a better approximation. You can feel free to pause and read and follow through. You can see here that they're using the trapezoid rule and the midpoint rule to approximate 1/x natural log of x, 1/x dx. Now we know that the integration of that is natural log of x. So when you go from 1 to 2, they give you an exact answer down here at the bottom. And this is the answer they come up with, the midpoint, and this is the answer they come up with the trapezoid rule. So take a minute, work through those examples, and pause this video, and then come back when you're ready. We know this isn't exact, so we say that there is an error involved, and the error from the trapezoid rule is equal to the real integral from 1 to 2 of 1/x dx minus 0.695635. And that helps us come up with our error. So there's a part in the book, and it walks you through what an error looks like. Find the error, because that's what's important, is how far off is it, because if you're going to have to use it, you need to be as close as possible. So here you see the formula for the error bounds. It says the absolute value of the second derivative is less than or equal to k. for A is less than X, which is less than or equal to B. If the error from the trapezoid rule and the error from the midpoint rule are the errors accordingly, respectively, then you have formulas here. So let's look at how this works. We have the error with respect to the trapezoid rule. Now, A and B are your bounds, and N is your number of rectangles that are given to you, or number of approximations. So the last problem, we had the integration from 1 to 2 of 1 over x squared dx. That's the one that they did. And they let n equal 5. Let's go back. So you can see here, n equals 5, a is 1, b is 2. And they figured the trapezoid rule to come out to be this value. So we're going to say the error with respect to the trapezoid rule is the absolute value of the error is less than or equal to k times b minus a to the third over 12n squared. So absolute value of e sub t is less than or equal to, let's do the easy part. Here we have k parentheses. B is 2 minus a is 1 to the third over 12 times n, which is 5 squared. Now let's talk about the k. Let's go ahead and simplify this and we'll come back to the k. So 2 minus 1 is 1 to the third is 1, so we have k over 12 times 25. That's 300. Now if we talk about k, k comes from right here. So it says f double prime of x. Well, in this case, f of x is 1 over x. So we need to find the absolute value of f prime of x is less than or equal to k. So f of x equals 1 over x. This means the derivative, by the way, that's x to the minus 1. The derivative is negative x to the minus 2. And the second derivative is 2x to the minus 3. So we basically have 2 over x to the third. So let's go back to the original function. We know that x values are bounded between 1 and 2. And think about your f of x. That's your y, which is 1 over x. When x is 1, y is 1. And when x is 2, y is 1/2. So that means that my y values are less than or equal to 1. It doesn't matter what it's between. I just need a number large. I need a upper bound for that value. So f of x is less than or equal to 1. And since f of x is less than or equal to 1, then the absolute value of f prime of x is less than or equal to, and we have 2 over x to the third. So let's call that 2 over 1 to the third, which is 2. So f of double prime of x equals, the absolute value is less than or equal to 2. So 2 is our k value. That less than or equal to came down from right here. It carries down. So that means we can put 2 in here for k. E sub t is less than or equal to 2 over 300. So the absolute value of e sub t is less than or equal to 1 over 150. That's approximately 0.006 repeating, or 0.067, whatever you want to call it. Now that's smaller. We know that this is the real integral, and this is the trapezoid value. So the error there is 0.002488, which is smaller than what we have. But we've approximated the error, and that's a necessary value. So you need to practice your trapezoid midpoint rules, and then come back and pick up the next video for the Simpsons rule. Thank you.